Hey guys, this is my lab 1 on charged tapes. So this is a table of contents we're going to run over. So in terms of the introduction, the purpose of this lab was to estimate the amount of excess charge on a piece of charged clear tape by running an experiment where we created multiple charged pieces of tape. We could then observe their interactions and calculate the excess charge. Our experiment could then be compared to a computational model for any discrepancies or sources of error. In terms of the results, overall, I was pretty surprised at how much stronger electrical force was than gravitational force. I knew it from lecture, but to see it in person was very interesting. You had like the entire Earth's gravity being canceled out by a piece of charged tape. In terms of the physics principles used, only electrical and gravitational force were used, as all other forces are not accounted for within the experiment or not coded for within the computational model. So gravitational force, we had force due to gravity, and then for electrical force, we had Coulomb's law and electric fields. So the actual experiment itself, we had two pieces of U-tape with one being held up by two stands and one under it. Since they have the same charge, one will repel one and make the top piece of tape seem like it's floating. At this instance of floating, the electrical force is equal to gravitational force, and that's how we're able to calculate this excess charge. So in terms of initial conditions, it's 8 inches or 0.2 grams, which means it's 0.0002 kilograms. The separation distance was 0.02 meters, and the system's the floating tape, while the surroundings is the earth and the tape being held. So in terms of the actual coding, I know Lab 0 had us code for a similar thing and expected us kind of use a similar code. However, I thought it was easier, instead of using functions, to just use variables and kind of code chronologically in terms of what we're calculating. So as you can see on the right, the red ball indicates the top piece of tape, the blue one indicates the bottom piece of tape, the green arrow indicates the R vector, while the orange arrows indicate the electric fields at both points. So we have our constants here. This is where I specify the charges and the spheres. We have all the R vectors, our hat, our mag, and our arrows here, and then gravity, equation, the charge, and the electric force. And then on the right, we have the output of my code as well as the image that I've been referring to. So in terms of the actual results, the magnitude of charge on the first piece of tape was not this. That's the magnitude of electrical field. The magnitude of charge is actually this, which is 9.4 times 10 to the minus 9th coulombs. So in terms of assumptions used in our model, air resistance being ignored was not an assumption. While we did kind of ignore all of their forces, air resistance specifically wasn't ignored. It was just that, air resistance wasn't even a part of this lab. We didn't have a moving object in a kinematic scenario where air resistance would have caused a change in the answers. We did treat both tape as a point charge with their charge centered at the center of the tape. This just made it easier due to the multitude of charge in the tapes to consider it one main net charge. And then assuming that they have the same net charge just made it easier in calculating the magnitude of the electrical field and gravitational force. So we did assume that as well. And as I said before, the tape is 8 inches long, 0.23 grams, 2 centimeters of distance. So the magnitude of gravitational force found and the magnitude of electrical force found was 1.99 times 10 to the third. As you can see, the computational model also calculated this the same. And this is because at the time that it starts floating, the gravity is equal to the electrical force. So for sources of error, there was just a few that I could see arising. The first one was just not accounting for a force that we were assuming is negligible. So if there's a force that is doing more work on the system than we expect it to, it could skew results. Assuming that you're maybe handling the tape too much, you could possibly dissociate the polarization or the charge on a piece of tape, making its net charge not equal and skewing the results. And then one thing I did want to note about sources of error is that you could also have factors of too much humidity or a gust of wind in the room you're performing this that could skew the results. So there's quite a bit like a chance for source of error, but I don't think any of these apply to this scenario, except for maybe touching the tape too much. And then the what if and what does it mean? So if electrons and protons switch the signs of their charge, so essentially, I thought that even though you're switching the sign of the charge, the magnitudes are the same, and since you're calculating the charges, when you have the two same charges, they're going to be squared. So since it's the same magnitude and the sign's going to cancel out when you square it, the calculations won't change in either direction or magnitude. And then why is it important to hold the charge tape as low as possible? I kind of went over this in my last sources of error slide, but essentially you could mess up the polarization or field by grounding the charge from the tape. Since you are electrically neutral, these charges could flow into you, making the tape neutral, which could then ruin the experiment.